Welcome to MECH2070. It's this term now you get into real machine design elements. Last year it was a lot more general mechanical engineering things because some people go in more into automation or into plant engineering. And now this year we're finally getting into the machine design components. Okay, so in this course we are going to get into all these components that we use basically for transmitting power from one device to another. You know, the biggest reason, at least in this course, that we make machines is to do things. And to do things, you need to get power to those things. You know, sometimes people build machines just because they look fun to look at, but we like to accomplish things for them. And so we're going to start off by looking at calculating the power and force and torque. And you know, you've done that in your physics classes, but now we want to actually bring that in to our apply it to these machines. And so I found previous years that if I didn't spend a bit of time looking back at power, force, and torque, when you jump right into these other components, people are like, oh, torque. Yeah, what is that? Like, even though in physics you learn moment arm, but then to translate that into torque in this class, it seemed to be a bit of a challenge. So that's the first area we look at. And then after we do the power, force, and torque, then we'll get into these various components like your belt and chain drives, your bearings, your shafts, keys, gears, and then we'll be looking at a design project that involves different drivetrain components. Okay, so looking first now at power, force, torque, and work. So the first thing we want to do is look at the idea of work. Okay, so work is basically force times distance. That's the simplest version of it. And another way to describe this is your change in potential energy. Okay, so if you had a box and you're going to push this box along the ground for 5 feet, and you have to push with 40 pounds of force, then your work is your 5 pounds times your 40 feet. So that gives you 200 foot-pounds. So that's your work done. And you're like, foot-pounds, well, that's some weird unit. Well, we'll get into more normal units in a little bit. But this is so foot-pounds is one of the very traditional forms of work units. Okay, so another example here. Let's say, you know, this summer you've had to do a lot of shingling or something. And so you're lifting bundles up to the roof. And then you're going to do shingling. So you've got a 75-pound bundle of shingles. You know, that's a pretty big hunk that you're throwing over your shoulder. And then you're climbing up the ladder, and you're climbing 10 feet up the ladder, okay? So you've done 750 foot-pounds of work just to lift that bundle of shingles 10 feet in the air. Okay, so here's another example. We are pushing a block up an inclined plane, and we want to figure out how much work we've done pushing it up that inclined plane. So we're going from a start position down here, and we're going to a finish position up here. Okay, and we got this 50-pound block, and we're going to push that thing all the way up. Okay, so we've got the, you know, back here we said the work is force times distance, right? So if we use that idea, then we're going to have to figure out how much force we're creating to push it up this thing. In your physics classes, you probably learned blocks going up frictionless inclined planes. So you would push it up that, and it would be going up 20 feet. So how much work is that done in the force times distance? So looking in the force times distance method here, to figure out the force, we've got this block, we got 50 pounds, and since we're in the metric or imperial system, that's just 50 pounds, and we've got 15 degrees, so our force is 50 sine 15, okay? So 50 times 15 is the force. Now the distance, we use some trig here, and so you got the 20 for the height, and you got the 15. So we got our formula here, sine equals opposite over hypotenuse, right? So that would be the opposite. That's the hypotenuse. And in this situation, we want to figure out the hypotenuse. So we rearrange that formula. So we got hypotenuse is equal to opposite over sine, and the hypotenuse is actually the distance. So that's the distance is, so we've got 20 over the sine of 15 degrees. And so now we got force times distance equals 50 sine 15 degrees, 20 over that. And it gives us the 50. And so those sine 15s are going to cancel out. So 50 times 50. So we got our 1,000 foot-pounds of to push it up. So that's using force times distance. Or we could just look at the change in potential energy. So with the change in potential energy, we could just go weight times the change in elevation. So with the weight times the change in elevation, we've got, we go back up and look at this guy again. So you got a 50 pounds here, and a change in elevation is 20 feet. So the weight 50 is lifted 20 feet, or its eventual change is 20 feet. And so that gives us 1,000 foot-pounds. Now that theory, the change in potential energy, works because this is frictionless. If it had friction, then energy is being lost due to the friction that's being created, and so we don't have the same clean system. So you can't use change in potential energies when you have a friction system. You can only do it in a frictionless system. Okay, so let's take a look at another example of work here. Okay, we got a barrel that's going to roll up the hill. So we've got a start position here, and we're going to roll this thing up 100 feet. And it's got a 5-degree incline plane, 5 degree. So going back to that old one, and when you're rolling, you're not creating friction. Well, actually, you sort of want some friction on there so that the thing doesn't, well, especially if you're walking up this thing. But friction is not causing a loss of energy because you're rolling and you're not fighting against that friction. You're not like rubbing against the friction. So it's the rubbing against the friction that would cause the loss of energy. Okay, so we have our force generated here. So the force concept, even though you're thinking, oh, rolling, okay, well, how does that work? Well, it's very similar. To keep this thing from rolling back down the hill, like you have your normal force, and like you can break this thing down into the forces. Right? You have the 75 pounds going down, 75 that's going down, and then when you start doing the trig on that, well, you've got your normal force here, which that's not stopping it from rolling down or causing it to roll down the hill. It's this here part, which is the opposite, like as far as in the trig. You got your hypotenuse and your opposite. So it's your opposite component which is making it want to roll down the hill. So for us to push it up the hill, for us to go up the hill, we have to go against that opposite force. So that force is the 75 sine 5 degrees. And back here, we said that we're going to go a distance of 100 feet up the hill. Okay, that wasn't the vertical distance. We said in this, the way they would measure it here, we said like the length that we're going to be rolling this thing is 100 feet. Okay, so we can just plug that distance right in there of 100 feet, and we get 653 foot-pounds of work that was done. Okay, so work is it's an okay concept, but we like to get work done in a certain amount of time. Okay, that's we don't want to just wait for the whole world to change and all that. The big thing is cars drive down the highways at certain speeds because they want to get certain places in a certain amount of time. If we weren't worried about that, we could just I don't know, wait for the wind to blow us the right direction. So power is the whole idea of work being done in a certain quantity of time, okay, in a certain unit of time. So then basically the more power you have, the faster you can get work done. So let's take a look back now. So now we're looking at the example that we had before, 75-pound barrel, 100 feet long, 5-degree incline plane, but we're going to go up that thing in 8 seconds. Okay, so see, you divide by some time unit to get your power. Okay, so we have your 653.33 foot-pounds, and that's done in 8 seconds. And so that gives us 81.7 foot-pounds per second of power. It's like, oh, foot-pounds per second. Well, I've never heard of those units. Okay, well, we'll soon get to some standard units here, but we'll just do a couple more of these things here. So I'll go back to the one where we were lifting a bundle of shingles. So we had a 75-pound bundle of shingles up 10 feet in 30 seconds. And so that gives us 25 foot-pounds per second of power that was being consumed. Okay, so
Sure.
what are the, yes?
I have a doubt.
Have a question?
Yeah.
Yeah.
So you said that work can be defined as the change in potential energy, right?
Yes.
So if you know the potential energy equation is mgh. So if can we do it that way, like at particular height, like 20 feet, the value of potential energy is different, and at ground level is different. So can we do it that way?
Yeah. So MGH, that's a metric one.
Yeah.
So where you have your mass and your gravity and your height, right?
Yes.
So these examples so far, these were imperial.
Mm-hmm.
So imperial, where you have it in weight is actually your mass times your gravity already.
Oh, yeah.
Okay.
Yeah.
So yeah, the weight is the equivalent of
the mg, right?
Yeah, mg with mass and gravity, mg together, you get newtons. So
Yeah.
newtons is actually the force.
Pound.
Yes, newtons is similar to pounds as far as
Metric and
because
imperial.
yeah, because that's what the newtons is the amount of force that the earth is pulling you down with, and just like pounds is the amount of force that the earth is pulling you down. Okay.
Yep.
So yeah, the two systems, they get a little messy, right, when you got to go back and forth. And we'll do some examples to them in both systems. So we just did a couple of examples in the imperial first there. Unfortunately, in Canada, you're going to have to work with both imperial and metric.
It's okay. That's fine. Yeah.
Like I remember when I was in like public school. So I would have been in public school in the 80s. No, in the 70s. Okay, I was in public school in the 70s, and they're bringing out the metric system, right? And I can remember them changing the speeds of the signs over to kilometers per hour, and they're like, "Oh yeah, the all of Canada is going to go metric, right?" And we still haven't. Like particularly in machine design, we are dealing with, and even in houses, right? You buy a 2x4, right? And you build things, and the sheets are 4 foot by 8 foot sheets of plywood. So unfortunately, we've never really transitioned because our biggest trading partner, the US, continues to insist on being largely largely imperial, and we are really, really closely tied to them, as whether we like it or not. So we have to teach both systems. Okay.
Thank you.
So
thank you very much.
Yeah, you're welcome. So we've got common power units. So the one we were looking at there, foot-pounds per second, and then probably you've heard this one, horsepower, because often horsepower, that's discussed in for cars, right? You know, you have a or say you have a motorcycle or something, you'll often talk in horsepower. And then you have a light bulb, and it'll be in watts, so that's another unit of power. And then when you see your power meter at your house, it's in kilowatts. So you've got all these various units here. And now what I've created this document. So I'm going to flip over here to my Econestoga. I don't seem to have it open, so I'm just going to open it up here. Conestoga. I thought I changed that picture. It didn't want to change. Okay, well, this one's changed. So on Conestoga here, under course resources, and I will be building this up more as we go along, but we got this document here, power working force, okay? So this will help you sort of navigate around some of those different units that we're going to be using, and when you got to go back and forth between them. So we'll go back and forth often to this document as we convert things. Because yeah, we're like, particularly this first day, all these different units are coming at you and you're like, what in the world? So think about that today's lecture, we're dealing a little bit with concepts, but more it's okay, we're going to get a little bit of comfort with all these units flying around. Okay, going back to this lecture here. So we have now horsepower is based on the amount of work a horse could do. And this concept was developed back when steam engines were first being used to replace horsepower. So I've got a little link here. I'm going to see if this actually works in this app. And now, can you guys hear that audio? Okay.
No,
we can't hear it.
You can't hear it. Okay. How about, can you guys download that PDF from my site and just watch that on your own, and I'll come back in 10 minutes? Can you guys?
okay.
Okay, so if you go to this site here, go here and go to theory, click on this guy, and we'll see if the links work right in here. So flip down to where we're at and click on this guy, and it should open up the link for yourself. Okay, so you guys do that, and then at like 11:33, so 10 minutes from now, I'll come back, and I'm assuming that you guys will all have watched that video, and then we can actually, I'll sit and watch it too. You guys watch it on your own, just clue me out, and then we'll get back to this. Okay.
There's no sound coming through.
I also can't hear anything.
I think you're muted, like we can't hear you.
Okay, what about, can you hear on that one now? Can you hear anything?
I hear you.
Yeah.
You can hear on that one?
Yep.
Okay, and I'm going to switch back to this one again. Can you hear me now?
Yeah.
You can hear? Okay, so I just had to switch back between the different ones, and then I came back. Thank you for letting me know. I wouldn't want to like kill the whole next hour just talking into nothing. Okay, so looking back at this example of rolling up a 75-pound barrel up a 5-degree incline in 8 seconds. So previously we figured out that that was going to be 81.7 foot-pounds per second. Okay, so that doesn't really mean much, but now when you look at it into, as far as the horsepower goes, okay, it's 0.15 horsepower. And that begins to give you some idea of, okay, so if you had a horse pulling that barrel up the hill, how quickly could he pull it up the hill, right? So he could pull up a lot more than, you know, because a horse, basically a horse can pull up one horsepower worth, right? So this would be pretty easy for a horse. Okay, so now let's look at another example. If you were as strong as a horse, which, yeah, that's basically all they are is muscle. Well, they're pretty nice too. I think they're a little temperamental maybe. So if you were as strong as a horse and you had to lift a 75-pound bundle of shingles up a 20-foot ladder, how long would it take you to do that? So we're just going to rearrange that formula, because earlier we said that power was, we had power equals to work divided by time, right? So up here, you know, when we first started looking at it, it's, well, force times distance is, or your work done over time, right? So we can just rearrange that now to have to figure out the time, it's going to be the work over the power. So we got 750 foot-pounds of work that's being done. And then if we're a horsepower, it's 550 foot-pounds per second. And you're like, okay, so where did I pull this out from? Okay, so this here definition, I've got that with that whole collection. It'll just take me a second to find it again. Yeah. So back here, when we course resources, and your so I've got here power horsepower is foot-pounds per second over 550, right? So that's where that definition comes from. So that's yeah, you know, foot-pounds per second over 550. That's, or 1 horsepower equals 5. Oh, I did a little typo here. See, this should be, see, I fixed it up here, but here it should have been, that should be a 5 in there. I'll have to fix that. Let me make a little mark in on my, I'll upload the corrected one after class. 550. Okay, 550. There we go. So so we got the work of 1500 divided by 550. So that gives us 2.72 seconds it would require to get that thing up the hill. Okay, so James Watt, that person that was mentioning in that video, so he was, you know, he invented the steam engine, or he at least got the thing rolling. Oh, terrible fun. He got that thing going, and thank you. So he came up with his example here. If you've got a horse could pull 150 pound, apply 180 pounds of force on a turning mill. So a turning mill, like when they would mill their flour, they would have these two big cylindrical objects, and they would be sitting on top of each other, and then the flour would be inside it, and it would be ground down to what we call, like, ground the grain down to a flour, and then they could make stuff. So they have a mill to do that. So let's use, previously they would use a horse to do this, and if they get the right lever arm, then he'd only have 180 pounds of force. And let's say he could go 144 times an hour. So this horse, he's just all day long, he's just slowly going around. It's not very exciting life for that horse. So I'm glad I'm not a horse for that. So he's going to be going around that 144 times an hour, or 2.4 times a minute. And this is going to have a radius of 12 feet. So let's take a look at the power that's generated here. Try to edit that too, put a little space in there. Power generated. So it's going to be force times distance over time, right? That's the basic idea. Now, okay, so what do we use for the distance here? And this here, so we've got your radius, and you've got 2 times pi times your revolutions per minute, times per minute, right? Yeah, 2.4 times per minute is revolutions per minute. So this here is your distance here, and then that whole thing is your distance in the unit of time, of distance in a minute, right? And then divide by 1 minute. So that's that way you got your force and your distance, and you put those together, and you get your power generated, okay, in foot-pounds per minute. But we've got another little formula here, I think, on the foot-pounds per minute. Well, you can just do the 550 times 60, right? And you get 3,300. So that's the easiest one. Like it's sort of in here. It's in here in this one, but your velocity in feet per minute times your pounds. So that's basically the same formula we've got, but it's maybe because of the fact that it says velocity here, it gets a little bit confusing. But yeah, you basically take that. You take your 550 here, and since we're dealing in minutes this time instead of seconds, it's your 550 times 60. It's going to be that in that, and so that's how he got basically 1 horsepower. Okay, he rounded that guy up and to this number. He says, okay, yeah, that's pretty close. It's a little easier number to work with than something like that, because the amount of power that a horse has, it's a little bit vague, right? Depending on the type of horse. So he just rounds that up, and he makes, he creates this definition of what a horsepower is. There we go. So we've looked a bit of power. And actually, before I jump into this next thing, I'm going to give you a little sneak preview of in assignment 2. Okay, so let me pull up assignment 2 for a minute. Now, assignment 2 is going to change. I'm going to clean it up a little bit, but I'll pull up last year's assignment 2, and then we'll see from that. Assignment 2. This is last year's assignment 2 here. Okay, so the first question that we have in assignment 2, let me zoom in a bit. We have this person that looks very, 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 very focused here, right? So this person is cranking on this handle. And as they crank on this handle, they're going to lift this, this is a tent trailer. Okay, so they crank on the handle and the tent trailer goes up. So, you know, we figure out what the import torque is. So the torque, to figure out that import torque, we have, the crank has an offset of 25 centimeters. So basically the distance from here up to here, that's 25 centimeters. And then he's applying a force of 30 newtons, okay? So he's pushing it around at 30 newtons. Okay, so that's very similar to what I've just shown here in this. In this example here, it was 180 pounds of force, and it had a 12-foot radius. Okay, so we use that information, the 180 pounds of force and the 12-foot radius. We use that in this formula to figure out the amount of power generated. Okay, and then later on we can talk about the torque too, right? Because the torque is just your force times your moment arm, right? And in this question here, they're asking, okay, so what's your force times your moment arm? Like your input torque is your force times your moment arm, okay? And then it asks for the work done in the machine, okay? So looking back at this example, the work in 1 minute, the work done in 1 minute is that, okay? And like in this example, it's going to be in metric units, so you can think about that. But yeah, we're seeing here the force in the moment arm, and then that's how you'll go through and solve this question. That's an assignment too. Because it seems that for some reason I get a bunch of questions. People, you know, they start doing this question and they're like, okay, so how do I figure out the torque and how do I figure out the work on this one? It's like, well, it's right here and here. Okay, and if you look back to this example, then you should be able to hopefully see the similarities and start doing that. I have the assignment 1 posted already. Assignment 2, we'll get that posted in the next day or so. Okay, so that was for power. And then we also want to deal with torque. Often in this course, we're actually going to deal with torque more than we deal with power. So we have to use a certain amount of power. Like we'll have a motor which has got a certain power rating, or you know, this system puts or generates so much power. But what we need is we need to break that power down because the torque is actually what heads to like twist our pieces of our shafts and destroy things. So the torque is is what we're going to pull the torque out to make sure that we don't break things. No, sometimes I know other people like to break things a lot, but us mechanical engineers, we like to sort of keep our machines together most of the time. So it seems about better. I worked in engineering for a lot of years, right? And it is a little bit fascinating when things do break. So unfortunately, when things break and they're at the customers, you've already built the thing and you've delivered to the customer, and now it breaks. It's you know, it's dangerous. You might get in a lawsuit and people start blowing up. So it's a little bit, you know, from an interpersonal point of view, machinery breaking is sort of crappy. But from a technical point of view, it's really fascinating because you get something that's broken, and then you got to figure out, okay, so why did this happen? Because we don't want it to happen again, right? And so you become Mr. Inspector when when you can get away from deflecting all that criticism because, you know, they're about to sue you, but you become Mr. Inspector and trying to figure out, okay, so why did this happen? So the braking part, it can be fun, that you try not to do it every day. So torque is force times moment arm. So in this situation, we've got 180 pounds of force and we've got our 12-foot radius. So we put those together and we get 2160 foot-pounds of torque. Okay, so then together now we get our power is going to be our torque times our rotational speed. Okay, so we're getting some ideas now of torque and power put together. And you know, back in the, oh, there's another spelling mistake. Oh, diesel has an E at the end. Diesel. Okay. So he was talking about the difference between those like really fast sports cars and like a tractor, right? They may have a similar amount of horsepower, but their torque is vastly different. Okay, so this is another example that I have of one here. So Mustang Cobra engine, it's got 354 foot-pounds of torque at 560 RPM. Or we have a Caterpillar engine. It's got like 1650 foot-pounds of torque, but at a lot slower speed, 1,200 RPM. Okay, so we've got a formula here: power equals torque times speed over 5250. And if we flip back to here, you see 5250, here it is, yeah. Power, there it is. I guess this doesn't really like to highlight very much. Power equals torque. So power, torque in foot-pounds times speed and for speed in RPM over 5250. Okay, so you're probably wondering, you know, when I pulled this out of the air, it's like, okay, so where did that come from? It came from that table there, from that formula sheet. Okay, so we've got our Mustang. It's going to have, you know, 377.6 horsepower. And so because it's got a low torque but a high RPM. And then with the Caterpillar diesel, it's going to have 1650 foot-pounds in, so it's got a lot more torque, so it can get that thing going, but it's not going near as fast. Okay, like, you know, driving down a transport truck, or when a transport truck begins to take off, it's like painfully slow trying to, you know, because it's just so slow getting going. But it can haul a massive load. So it needs that torque to haul that massive load. Okay, so both of these engines, they actually produce about the same amount of power, right? One's got a high speed, low torque, and the other's got a low speed, but a high torque. Now, the amount of torque, we can see this a bit better. And I've got a little video here that gives you the idea where you can actually visually see on the truck. We'll see the front end of it, the end, it'll twist. The front end of the truck will twist as it pulls up here. So let's see here. So you guys pull up this video in your own thing. Was it? It's like. So I will. Yeah. Well, it'll take about 5 minutes for this video, and then we'll. So yeah, pull up your PDF again, and watch this video on your own. I'll be watching it here on my own, and then after that, we'll probably have to, you know, get the sound thing working again after this guy. Okay.
So the reason why like cars, trucks, etc. always lean over to the right when like they start to put power down is because they're trying to spin the output shaft, which spins to the right, and then there's some resistance at the wheels, right? So it tends to rotate the entire vehicle towards the right. Is that correct?
Okay, let's see if we can get this working back here. I'll switch between. Okay, is my audio back?
Yep.
Yeah.
Yep.
Okay. So you guys you guys all watch that video? You see how those trucks, the front, particularly the driver's side of the front wheel, it would pull up. Okay. So there you're seeing torque, because that engine is basically the engine. It's twisting the drive shaft, and you know it's putting power back to it. But all that twist has to come back to the actual frame of the truck, and so that the truck will twist the truck frame twists in the opposite direction from the way the shaft's going, because it's, you know, it's got to drive it, and it eventually goes to the back of the vehicle. But that the frame of that, it's got to resist that. It's got to resist because see, if there was no frame there, the engine would just like spin around, and it would fly right. It would just, yeah, spin around like a propeller, right? And that's in car or in planes, you know, the propeller just spins around. Well, the engine is held secure and the propeller spins around, but the engine would actually just spin. There was a concept called a Rankle. There's rotary engines. There's a couple, like in the Second World War, they had some types of rotary engines. The engine would actually spin. It was meant to. But yeah, you can see that this situation, without the restraint of the frame, the engine's just going to twist, and even with the restraint, it still twists a bit, enough that you could see it lift up. So that's neat. You get some idea of the amount of power that's going through there. Okay, so now we're going to start working through some examples here, and these examples, they're a nice little warm-up for because I've already posted assignment 1. If we flip back over here, course content. So we've got assignment here. So assignment 1, and this first assignment, you know, you'll be able to do after today's lesson. So I've got a very simple one here, but it's in metric of pushing a block up a hill. I just want to begin to get these ideas in your head of power and force. It's just like, oh, okay, that's pretty boring. I know that's boring, but it gets you moving, gets your, you know, gets your fingers. Remember, you begin to remember how to use a calculator again. So, you know, little things like that. But then I also have another one in here of a car going up a hill. Okay, so we have a couple of examples. You know, these are different numbers than I use that I'm going to do in my lesson, but it gives you some stuff to work with. Okay, so we'll go through an example here of a car going up a hill, and we've got some weight, and you got some speed and a grade. So we're going to put all that together and figure out, okay, so how much power is required? Now, I should have said assuming no wind friction, because of course you need some type of friction. All these little things I have to correct as I go along here. No wind friction, right? It should be no wind friction here. Well, we'll get that cleaned up for the next one. So what is the power required assuming no wind friction? So we have grade equals rise over run, and that's 6%. So grade, yeah, so rise over run. So if you just assume like a run of 100, then because it's percent, right? Percent is per 100, but that's what percent, that's what this here, like that's what percent literally means, per 100. So it's 6 up per 100 of run. That's what the grade is. So that's going to give us we want to do the trig on this thing, but for trig we needed angles instead of grade. So we do the arctan, or the tan inverse of 6/10, and it gives us an angle of 3.433 degrees. Right? So that's going to be the degrees in this situation. Okay, when when you go to doing your assignment, I would give you a different grade, I think. Yeah, I give you a 10% grade just for something different. So it's going to be a different angle. Okay, so don't try to just take the angle from here. You're going to have to figure out your own angle again when you do the assignment. So we've got the grade, and we got this thing in 50 miles per hour. And I have to figure out power, right? So we might want to look at some of all these formulas that I had here, and see, is there one that had, is there one that had miles per hour? Let's see here, power in miles per hour. No, you could make one yourself, but see, I gave a power that had a force and a feet per minute. Okay, feet per minute, we have one here, or foot-pounds per second, but we don't have miles per hour. So since we don't have that, what we're going to have to do is we're going to have to take this 50 miles per hour and we convert it. So we convert it to feet per minute. Okay, so if you have, you have Dave Springford's classes, so then he's going to hammer you in on making sure you do all your conversions correctly. So we start off with your 50 miles per hour. So that's what you get there, 50 miles per hour. And then times 5280 feet per minute. Now I've given that little number on here too, right? A mile is 5280 feet. It's because it's like, I know, like probably until you got to college, you're like, but I thought I didn't have to know all these like weird little details. It's like, well, unfortunately, you gotta know all these weird little details. So 5280 feet is a mile. So we're going to convert the miles to feet here, but we also had it in, this was miles per hour. So we got to convert the hours to minutes. So you see that since initially the miles was on the top and the hours on the bottom. So when we do these, oh, there's another typo. That should be in, that should be per mile. Okay. So that should be feet per mile and then hours per minute. So I'll get that fixed up also. So what we end up getting out of this whole thing is 4,400 feet per minute. So that's our velocity in our, now we have it in the units that'll work. We have feet per minute. So we'll be able to use it in that formula. Now this also asks for force. Right, so we gotta go through and we gotta figure out the force. Okay, so hopefully we're getting a little bit comfortable now with this whole incline plane thing and the forces from that. So we got our 300 pounds, and then we've got our angle 300 or 3,000 pounds, 3,000 sine of the angle, and it gives us basically 180 or 179.63 pounds. So we can put those together, right? Because the formula is force times velocity over 33,000. So we put those all together and we get our 23.93 horsepower to go up that hill. So that Bentley back in that, in the video, it was like 650 horsepower, I think it was, or 650 horsepower. So, if you lived in moderately flat areas, what was that, 6% grade? Yeah, like a lot of Ontario is moderately flat. You could get around with like a 24 horsepower car, if you wanted to, if you don't want to go super fast. Like what speed would this guy go on? 50 miles per hour. Yeah, you could putter around at 50 miles per hour, and you could get around pretty well at Kitchener-Waterloo area, right? You could probably get around here and survive in a 24 horsepower car, or you could buy a Bentley it's got like 650 horsepower. So it's beginning to seeing this stuff. It's beginning to get helpful of seeing the different how much power it needs, how much. My first Honda Civic, well, before my Honda Civic, I owned a Ford Granada when I was back in university. So it was probably a 78 Ford Granada. I'd bought it in 88. Yeah, and it's probably, yeah, about that. And when you'd go to a hill, or let's see if we can pull up a picture of a Ford Granada here. You know, I'm sure you guys are curious, right? So Ford Granada. So yeah, so this is basically the type of car I had, okay? This type of thing here. And so I was like fixing it every day. That's how I sort of earned my stripes, is so that in mechanical engineering, I not only can like design stuff, but I sort of know how to fix. I know how it's all put together, because this thing was like breaking down every day. But you'd go to a hill and you'd want to drive up that hill, and as you're you really need to like gear up or gear down, but also speed up, because you knew that, okay, like by the time you get to the top of that hill, if you had to be at least at the bottom of the hill, you want to be going a good 80 or 90 kilometers an hour, right? Because by the top of the hill, you're going to be going like 20 or 30 kilometers an hour, just because it's like, it got so little power. Okay, cars nowadays have way more power, so they're not like these ones. So this thing was a big, heavy vehicle, and it's like completely gutless. Okay, and then in addition to being completely gutless, they like consume tons of gas. If the engine, so we've got this 24 horsepower. Now, what if we got this engine and it's going at 4,000 RPM, okay? And we have 22-inch tires at the rear end, or at the front too. You know, we're not going to do like weird things. And now we want to know what type of a gear ratio we need if we want to maintain this speed of 440 feet per minute. Okay, so first we want to figure out how fast the rear tires are going. Okay, so let me just add a little note onto this one too. We want that to say rear tire RPM. Tire RPM. Okay, this first presentation I'm doing here, this was a already created PDF document, and unfortunately I can't edit it as I go. Soon I'm going to be moving to, I think I'm going to be doing OneNote with my later ones, so then I can like make changes as I go. I've been playing with different types of technology of how best to do it, and this was my first attempt. I created my first lesson in this one, and then we'll create the later ones in a little bit more interactive method. Okay, so we have our RPM, speed and circumference. So the speed we have on the top there, up, and then the circumference, we want to make sure the circumference is in the same units as the speed, right? So the 22-inch, we got to convert that into feet, and then times diameter. Pi times diameter is your circumference. So we've got 763.9 RPM for the tire. But we wanted to have the engine running at 4,000 RPM. So out of those, we can figure out the gear ratio. So our input speed, that's going to be the engine speed, and the output speed will be the speed of the tires. We put those together, and we get a gear ratio, overall gear ratio of 5.24. Okay. Now, it's also nice to figure out the engine torque. Okay, so the engine torque here, it's one of these ones that we pull up here. So we find one that's got torque here, and power, horsepower. Foot-pounds is nice, right? you know, for things which are bigger ones, we like to use foot-pounds. So we got foot-pounds, speed RPM, 5280, or sorry, 5250 RPM, or the conversion factor 5250. So we put that stuff together, and we have that formula here. And we want to rearrange that for the torque, right? So we've got the torque out the front end here, and it's going to be, so we got torque or horsepower times your 5250 over your RPM. You know, we just rearrange that thing so you got your torque out there. And so you got 31.43 foot-pounds of torque. Okay. Now, I should just, since I noticed someone else coming in that I admitted, I should make sure here that I've got, do I have my, got 19 participants. Let's see if I can see what my chats are here. Make sure that everybody is at least, so I've got 6 chats. And come on, you can show that, can't you? Oh, no. Okay, I want to make sure that everybody says at least hi on their chat, because then I can try to figure out how to record that, and then I can know who actually showed up today. Okay, I'm just trying to pull up my chat to make sure that it was. Yeah, we'll work that out a bit more at the end. Oops. Okay. So, yeah, for some reason my chats don't want to show up here, because I do have some people that have shown that have chatted. Alt H. No. Okay, so I'll keep on doing this, and then we'll try to get that chat thing figured out towards the end of the lecture. So we have 31 foot-pounds created. Oh, I didn't want that color. I like these colors. There. 31 foot-pounds created of torque. Now compared to, so, you know, we're back looking at the these diesels and things. So your Caterpillar, 1650 foot-pounds here, or even in your Mustang, the Mustang has 10 times the horsepower of that little car, you know, in our example. So you begin to get some idea the amount of overkill you end up getting with these vehicles. You get a lot of overhang. Okay, you get a lot of overkill. Definitely have to fiddle with this a bit more after class. So there we go. Was the imperial example. We got ours down to our power here, and now we're going to look at a metric version. So with this metric version, we have 100 or 1,200 kilograms. We have a velocity of 90 kilometers per hour, and we have a grade of 15%. Okay, so when we put that together, grade of 15%, we get an angle of 8.53 degrees. And then with that, we also need to get the speed into a unit, which is useful. So here, so the, and eventually, okay, what are we going to try to get? We're just going to do this whole thing in imperial, or sorry, in metric, okay? We're not going to worry about the horsepower ones, okay? So if we don't worry about the horsepower, then with the, with power, it's a lot easier with power, because watts is just a Newton meter per second Did I say that here somewhere? Yeah, a Newton meter per second, that's a watt, right? And a kilowatt is 1,000 Newton meters per second. Okay, so we just need to get our stuff into meters per second. Okay, so what was this in? I think it was in, did we put it in kilometers per hour? So we're gonna have to convert kilometers per hour into meters per second. So you got your 90 kilometers per hour, and then you convert that into meters, 1,000 meters per kilometer. And then, but you want to divide it because you want to go per second now instead of per hour. So you divide by 3,600. So that gives us 25 meters per second. Okay, so that's our velocity in a decent system that we'll be able to use with the watts, you know, the watt being a Newton meter per second. So we got our velocity now, but we need to get our force. Okay, so for a force, in this one, we need to do, this is the mass and then your gravity. We need to put those two together, mass and gravity. So that's your whole gravity force acting. 11,760 newtons is pulling down on it. And we have, though, acting, we really want to know the force that's making this thing roll back down the hill. So this here is the force that is actually, why did I do that? Oh, okay. Nope. I get too happy with my little pen here, and okay. So I've got that number down here below. The force is 1744 newtons, and then 25 meters per second. So we put those together, and we get 43,600 watts, or 43.6 kilowatts. Okay, and we'll do the gear ratio stuff with this one too. So with this, we need to find out, we take the speed and get the circumference of it. All right, and we got to figure out the wheel RPM here. So with the wheel, so the wheel RPM, we take our speed in meters per second, and so for RPM, so we want revolutions per minute. So we're going to have to convert that to, so times 60, so that we get rid of the seconds and we bring in minutes per minute. And then we got a diameter. In this situation, I said is a half a meter of the wheel diameter is half a meter, and times pi. Okay, so that gives us 955 RPM at the wheel. So they put that together. We get the tire RPM and then the engine RPM, and then we get a gear ratio out of those of 4.71, and there's no units with that because it's just comparing a speed to speed, right? So the units cancel out. So how much torque is this thing creating? Okay, so for the torque, now for this we do need to go back to here and pull out. So we've got a torque here, a metric. So torque here times meters, Newton meters torque times n RPM. And now see, there is, like, you know, I think up here we could have, like, you're wondering, okay, so why in the world do you have this conversion factor in here? We're in the metric system. Okay, it's like, well, okay, like you could do it this way. You see this one here, power is torque Newton meters and radians per second. So if you do it in this, then you don't have to have a conversion. Okay, but that's per second. But you know, most people don't say, okay, well, you know, this engine was going 500.8 radians per second, right? It's like, what in the world? No, they go revolutions per minute. So revolutions per minute, if we're going to do that, then we need to use these numbers here, as a conversion factor. Okay, so we've got that conversion factor in here. And we can basically plug the number, rearrange this formula, plug the numbers in, and we get our torque of 92.5 Newton meters. Okay, so that is the torque that this example is doing in the metric system. Okay, so that is the end of the theory for the first day.